Hi, welcome to another video. This is really a continuation from the previous video. In the previous video I was looking at Microchip's parallel master port and how the address bus increments. Today I'm going to show you the struggle I had getting the external bus interface to increment. I got the external bus interface address to increment using the DMA, direct memory access. I'll show you the code. But first I want to go into some specific details on reading the data from the parallel master port. When you read data from the parallel master port, you're reading data that's 1 byte old, so you have to disregard the first byte and start with the second. I'll give you an example on this. This screen capture had a bug, and every time I capture the screen, some of the picture from this side would appear over here. Let me show you. Right, this is programming now. It's going to draw this picture. I'll capture this glass, and when the seconds get to 6, it will put that capture back. Right, let's capture the glass. Wait for 6. And there's the glass. That's something like 150,000 16-bit words there. So at a glance you can't see anything wrong. Every time these numbers disappear, that's this middle bit being redrawn. Now we need to wait for the picture to come round. Right, so now wait for 6 seconds. There we are. So it's redrawn that glass. But what's this over here? Now this is data from here. I've spent a long time looking, but these lighter bits are the lighter bits down here. Either here or here somewhere. So how do you get around this problem? Easy, just ignore the first byte. Except because I'm capturing 16-bit words, not 8-bit bytes, I have to increment the register by 4. I'll do that now. Right, so those 150,000 words were stored in a register, and rather than display them one to one, all I'm doing is ignoring the first 4 words. Now see what happens at 6 seconds. You can't even see it, can you? Wait for 6 again. So I'm happy I've got the capture working, and we haven't got any lines here from this side of the screen. So that shows the data you are reading is lagging what you're actually doing. Right, here's a section from the datasheet. So first of all, before I show you my code for that register, I keep on saying register, I mean buffer. I'm capturing the data to a buffer. So this is a section from the datasheet, and don't believe all you read in the datasheet. So this generally refers to the parallel master port, and when it is controlling the chip select, after it's controlled the chip select, the first read you see there is a don't care. And then you can see it's reading some data, it changes the address, so presumably the chip select is activated, which means the first bit of data again is don't care. So some of this makes sense and some of it doesn't. So here is my code. The chip select is being activated by me once and turned off when I'm done. The buffer size is 150,000 words, so 16-bit words, not bytes. That's important. I'm capturing 150,000 16-bit words here. Chip select on and off once. This is where I write back to the screen. So still 150,000 words in the buffer, and you can see here, to get rid of that bug, I'm starting at 3, which is actually 4, so 0, 1, 2 are 3 bits. I'm starting at the 4th bit. This doesn't make sense. This is saying you ignore the first byte. I'm having to ignore the first 3 words, 16-bit words. So the last bit of this parallel master port. In the last video I wasn't sure about the wait states. Here's an example taken from the datasheet. So I'm still not sure is these wait states apply when the microcontroller is controlling the chip select, which is this one here, chip select 1 or chip select 2. So that could be for your memory, for your display, any device. So when it has controlled the chip select, in this example, you're waiting 2 cycles before the read strobe. Then the wait M is 3 clock cycles. 1, 2, 3. So the wait M is important. That's the width of the strobe. And then 1 cycle before it turns the chip select off. So what the datasheet is not clear on is if you are controlling the chip select, what happens with wait B and wait E? Presumably nothing. So really the only important one is this wait M, the width of the strobe. If you strobe it too quickly, some devices might not recognize it as a strobe. In the previous video I discussed the parallel master port address bus counting up to 15 with 16 bits and the external bus interface up here being able to count up to 23. That's 24 address lines. And I showed you an example counting up to 65,536, and by controlling 1 extra port pin we could get that to increment to 131,000. But having the external bus interface, we've got 24 pins available. No need to mess about with port pins. So it's taken me months and months to get this EBI to increment. In the datasheet they show you an example. They have a pointer pointing to the address of the SRAM. I'll run through the memory map briefly. But the external bus interface has a virtual address starting here. So it gets complicated, but the datasheet and the example for incrementing the EBI address speak of the internal MMU, so Memory Management Unit, and a TLB, which is the Translation Look-Aside Buffer, which is all to do with the mapping of virtual addresses and physical addresses, which is too complicated for the topic of this video. So really the only basic thing you need to know is the EBI physical address starts at this address here, 2 and 7 zeros. So that's 536,870,912. That's the physical address of the start of your EBI. Well, here's another excerpt from the EBI datasheet. This is their example of incrementing the EBI, and it sounds straightforward enough. There's a pointer to the SRAM address, and the CS0 is a chip select for your first lot of memory. So there's a loop and the counting to a quarter of the size of the SRAM. And then incrementing the address here, there's the pointer to the address, which would be that number I showed you earlier, 2 and 7 zeros in hexadecimal. But what I don't get is this number here. That memory has only got 16 data lines. So they're writing this massive 8-digit number to each address and incrementing the address. Here on 16 data lines, you can only have that. FFFF, that's 16 bits. So there's the first bit I don't get. That. So as I say in their example, they write that for a quarter of the size of the RAM, and then they read it back. And if you haven't got the same value at each address, it fails. Otherwise it returns a success. That's straightforward enough. But it's this address plus. It's taken me months to get it to work, and whether it's something hidden away in their IDE that enables this to work, or something to do with the MMU or TLB not set in my microcontroller using a microelectronics IDE, I don't know. But this absolutely will not work. What does work is getting the direct memory access to do it for me. So back to my screen. I finished capturing 220,000 16-bit words to this screen, it writes it to the SRAM, and when it's finished I set the address to 1, just to illustrate I can control the address via the DMA. And it's a good job I've got these 8 LEDs for the lower 8 addresses on here. I'll reset this, let it capture the data. You'll see it increment the EBI via the DMA in a flash of a second. Remember, it's counting 220,000 addresses. It captures that data, writes it to the SRAM, and then reads it back from the SRAM, writes it back to the buffer. Let me unplug it and restart it. Watch these LEDs, and you can see these are the DMA flags. It's complete. That's the 220,000 16-bit words. And now it's finished, the address is on 1. So I've been chatting to someone called Paul about controlling a display via the external bus interface. So since the external bus interface has got 24 bits, you can control a 24-bit colour TFT. The normal parallel master port only has 16 data lines, the EBI has 24. You can swap the EBI around and use it to control data out to a 24-bit display. And you've seen the numbers, 24-bit, 16 million addresses, which will give you 16 million colours. Right, this is programming again, and I've got the address lines down here. This is 23 down to 7, then we've got the rest on the board up here. Hopefully it's all in view on this camera. Right, 220,000 ints, and I haven't reset the address to anything. But we have a look at these numbers here. So 23, 0, 22, 21, 20, 19, 18. So 17 and 16. I'll put these on a calculator and you can check it yourself. Go to Programmer View, Windows Calculator. So bit 17 and 16. 15 is a 0. 14 is a 1. 13 is a 0. 12 and 11 a 1. 10 is a 0. 9 and 8 a 1. 7 is a 0, and then 6 and 5 up here on the board, a 1, 6, 5, then 4, 3, 2, 1 are zeros, 4, 3, 2, 1, and then we've got a 1. That equals, on Windows Calculator, 220,001. So I was thinking, if I'm going to control a display via the external bus interface, no controller, just the microcontroller running a TFT 24-bit, so 8 red, 8 green and 8 blue, I need to know I can control all 24 bits. So I started incrementing the address. So we know it can count to 220,000 because we've got the picture here. This is address 262,143. So 23, 22, 21, 20, 19, 18, 17 down through 0 on. That's 262,000. Now this RAM is set to 512K, 16 words, so it should be able to count to 524,287. And that looks like it's worked. So 23, 22, 21, 20, 19, 18. And that's the maximum for my SRAM. Right, this is the next address up. This is turning on 20 bits. And there you can see these are all over the place. And my lower bits have gone off here. So although I've told the EBI controller I've got all 24 pins, my memory size is still set at 512K, so I need to extend my memory size. The next logical step in the datasheet, 16 meg, so I'll do that now. Well, I'll flash up the code on the screen. I'm now programming this, telling the EBI it's got 16 megs of SRAM. That's better. We've now got all the ones. So we still need 23, 22, 21, 20. These would be the most 4 significant reds. So you saw by having these LEDs on the board here, I could see there was a problem. So this is just over 2 million addresses coming on, 21 bits. They're all on, all the LEDs are on here. You can see all the ports are on. So 23, 22, 21, so 20 down to 0, that's 21 bits. Next address, 4 million. There we are, bit 23 and bit 22 are off, all the rest are on and all the LEDs are on. Well, I'm now programming 23 bits, which will give us 8 million addresses, or 8 million colours. So we're looking for this to come on here. And it's on. Leaves one more bit. Right, last bit, 16 million. So 16 million for 16 meg SRAM. Hello, this is wrong. So we've got half the LEDs off here. So if I wanted to turn on all the reds, all the greens, all the blues, that's what we have. I can't do it. Yet I've told the controller I've got 24 address lines. I've told it it's got 16 megs of RAM. It doesn't know any different. And this is what happens when you try and write 16 million addresses to 16 megs of SRAM. Something's wrong. Right, this is the last screen capture I'm going to do. The video's getting long. So this is my SRAM controller function. When you initialize your MCU, you initialize the EBI as well, external bus interface. You tell it the memory type, whether it's flash or SRAM, etc. That's easy. Then you tell it your memory size. Then there's 100,000 bits, whether you're using the EBI write enable and EBI read enable, and which chip select you're using, how many address lines, which is this bit here, CFG EBIA. This is where I told it I've got 24 address lines. These bits here are the additional pins for the read, write, etc. This one's important, EBI CS0. This is where you tell the EBI controller the base address. So I struggled for months because in the example they show it as a define. You define a memory address, and that's the base address as I showed you earlier. Nothing would work, ever. So not until I changed it from a long, unsigned long, could I actually get the address to increment via the DMA. So forget the define, forget the RAM size, you don't really need it. It's by making this SRAM address an unsigned long, you can then manipulate it. When you define it, you can't. You have to have a pointer that points towards it. If you have a pointer pointing towards the base address of your SRAM, you can increment it with the DMA. You still can't do it in a while one. I tried 101 or 1001 permutations over 3-4 months, and it absolutely will not work. This does work. This is my buffer size. You saw that last buffer capture, 220,000. This video is too long to get into the DMA, but you turn on the DMA channel, which is DMA channel 0. You have to give it a source address and a destination address. So my source address was actually the buffer. I had a buffer, this one here, my SRAM buffer, and I initially had it as an absolute address at A0. This is converting that virtual address to a physical address, which the DMA expects, otherwise it won't work. So although I'm not copying from the buffer to the display, I'm telling it that's the source address, which is defined there. The DMA can only transfer 1 byte at a time. That's another issue. It's actually quicker to do it my way and just use the DMA to increment the EBI. Each DMA channel, of which there are 7 or 8, I think it's 8, can transfer 65,535 or 536 bytes in any one go. 65,000 times 7 or 8 still will not fill this screen, so the DMA is actually of no use for this size screen, but the DMA increments my address. So that's my source address converted to a physical address. That's destination source there, destination size 2 bytes, destination address is my SRAM address, which works because I've defined it as a long there, channel destination size bytes register, channel DMA cell size register 2, turn the channel on and then enable the channel automatic enable bit. That's all you have to do for the DMA in this particular application. And it's not worth me messing about trying to get the DMA to transfer a picture the size of this screen, because tying all the channels together is still not enough bytes for this size screen, 800 by 480. So that's initializing the DMA to get it to increment the EBI, nothing else. Rather than using interrupt, I'm forcing the DMA here. So all these bits that took me, I don't know, hours and hours and hours or days to configure, half of them you don't need. And so that my screen will continue working, you have to disable these bits here. This is timing for 10 nanosecond SRAM. This is telling it you've got 16-bit data path, not 8. But what is important with this memory size? So this is from the datasheet. 16 megs, if you work this out in like binary, that 1, 2, 4, 8 plus the 1, that's 9. Yeah, that equals 16 megs. And you can't write 16 million bits to 16 meg of RAM, as you've seen. So I thought, have a look at the data sheet. I've done this. 1, 2, 4, 8, 16. Let's set it to this, and the data sheet hasn't got any size for this setting here. So let's program this memory size. There you go, that's setting that unknown memory size. And we've got all the bits turned on. 23 down to 7 and the rest on the board up here. That's odd, as you see in my program, copied from the datasheet, 16 megs is defined as like binary 9. If I define it as binary 16, I can write 16 million bits. I'd expect 16 megs to be defined as 16, not 9. It's all very confusing. So that unknown number, I'm setting it as 16. I can now write 16 million bits to the EBI and control 24 pins in a flash of a second. So that means I can control a 24-bit TFT. So controlling 24 pins seems simple enough when you get the DMA to do it. There's loads I haven't discussed and this video is too long already. So what I didn't mention is the DMA counts in bytes and will write 2 bytes before it strobes the read or write. That means your counter effectively divided by 2. So I'm actually, when I increment the counter in the loop for this picture, I'm shifting the count left by 1 place, which is multiplying it by 2. I'll put the C file on GitHub and put a link in the show more, give me time to do it. So this has been an introduction into the external bus interface and how to get the DMA to increment the EBI. It's not as straightforward as it seems, or not in my IDE anyway. So as I say, yeah, have a look at the C file if you want it. Go and grab it. You're welcome to make a donation for the months and months it's taken me to get this going. If you like it, don't forget to click like. If you've got any comments or questions, leave them down below. Thanks for watching.